Hey guys, what's up? This is Vale and welcome to my channel. Now in today's video I'm going to be explaining the stack frame and the stack by itself. The last couple of months I wanted to learn reverse engineering and exploit writing. So for that matter I went up in Google and typed those things, and I came to know that I need to really know how stacks and stack frames work, how each functions in a program works exactly in the computer to understand exploit writing or reverse engineering. So I went ahead and searched about stack frame in Google, YouTube, and whatever there is. So I went to this blog of something, I don't remember the guy's name. So in his blog, the topic was drawing the stack. So I started to study it, and I saw that the post was marked under a beginner. So I thought, okay, why not? I am a beginner, so I could get a lot of help from the write-up. So I started reading, and I actually saw that it was not actually really easy. One of the reasons being that assembly has a lot of versions. For example, x86 assembly is different in some way, x64 assembly is different, the syntax differ in AMD or Intel or AT&T. So there are different type of encodings, there is a different type of formats, everything is in hex or in binary. So it was actually a lot hard for me to understand. And on the other hand, when you study those things, and if you just believe whatever is written on the screen and you study line by line, it's okay up till that. But if you ever ask the question why, for example, why this is happening, how this is working, if you ask that, then there is not a lot of details that you can study from. So you already know from my previous videos that I go into a lot of depth in each of the topics that I take in. So in this case I wanted to learn stack frames, and there was not a lot of details in the things I got, and I am not actually a very good reader, so reading a book from the top to bottom wasn't my thing. So I actually relied on YouTube on visual feedback. So it was not easy for me. I went up and studied hundreds of videos and hundreds of tutorials, and I have came up to the conclusion, and I actually now understand stack frames pretty good. So that is what I am going to be sharing today. And this video is not going to be on computer screen mainly, but it will be on, I'm going to take my pen and paper right now. So I will be showing you the written version of what I'm doing, so I can actually do each of the steps manually and make you understand why I'm doing, where I'm doing, and when I'm doing it. So best of luck. I'm going to get my pen and paper, so let's start with the tutorial. Okay, now just before that, what is a stack, or what is stack frame? So in the RAM or in the memory, whatever you like to say, there is a specific portion of the memory assigned for temporary values, function calls, returns, local variables, etc. So this portion of the memory is called stack. And in a stack frame, so what happens in a stack frame is we take a RAM or we take a stack and we partition the stack into different regions, and each of these regions or each of these portions of the stack is assigned to particular functions. So in a program, if main is a function, then there is a different stack frame for just the function called main. If there is a function called add, there is just a different stack frame for the function add. So this is called stack frame. So again, a stack is a portion of the memory that is used to keep return values, calls, function calls, local variables, and the stack frames is assigned to each of the running functions in a computer or in a program, so we can allocate specific parts of memory for each of the programs, for each of the functions, for each of the functions to keep its variables stored in the memory, of course in a volatile way. So let's go ahead. I'm going to bring up my pen and paper and show you what exactly I'm talking about. Okay, so where was I? So stack frame, right? So what I can do is give you an analogy instead of diving directly onto computer terms. So let's say you have an inverted bookshelf. So say that this is a bookshelf, all right? Okay, not a very good bookshelf, but we don't care, do we? And there is another inverted bookshelf. So both of them have a lot of books. Okay, so let's number these up for ease of understanding. Now, say that you already have studied the 3 books from the bottom and you wanted to start here today. So now when you actually, and let me say that you wanted to read 4 books today, all right? So you immediately look at this bookshelf and you know that these are the 4 books that you actually want to study. So you actually make a mark here that, okay, this is going to be the end point, that I will not study anything above this line and I will not study anything below this line. Now, as a human being, your brain does these things automatically, but if you were a robot per se, then you would have done the same things, and that is exactly what a computer does. So let's say that this is going to be the start pointer, okay? So let's say start point, and this is going to be the end point. All right, so what happens is, when you start studying these books, a lot of things can happen. First of all, you have to remember the number of pages, the number of books you have read. So for example, when you are done reading this book, you know that this book is not you are not going to read this book anymore, so you shift on to the next book on the shelf. So what you actually do here is, let's say we give you a scenario that you have read this book, you have read this book, you are now reading this book, and in that book there is this particular maybe there is a particular chapter that is specifically saying you that to understand this point, go to the second shelf, 4th book, and on the 4th book you will know what you are looking for. So what you do is you take a piece of paper and write the number of book you are currently reading. So you can see that in the whole shelf of total 8 books, you were reading the 6th book, right? So what you do is write 6. So you say that this is what I am going to read after coming back. So I really hope that the camera is on focus. Okay, now it is actually. Nice. So you keep this little piece of paper and write down 6. So you are going to return on that particular book when you return. Now on this 6th book, you also see that you have to go to the second shelf's maybe 5th book. So you also write 5. Now what you do is, you have already written this 6 in a piece of paper. Now you leave this aside and go to the 5th column. So maybe 1, 2, 3, 4, 5. You go to this column, study the whole book, keep that book in the shelf as it was before, and then you come onto the table. Now you have already forgotten where was the last book you were studying. So that's the reason you have this piece of paper. Now you read that in a piece of paper there is 6. You immediately remember that this was the number that was holding the current book in the shelf position 6th. So you move on to 1, 2, 3, 4, 5, and 6th, and you take the book on the 6th page, on the 6th rack, and you start reading it. Once you are done reading it, you can keep the book back on where it was before, and you are done with reading the book, and you can maybe go to the next book, finish the reading, and maybe forget about that you have read anything at all, because you have already completed all the books in the shelf except the last one. So you can or cannot read the book. So if you want to read the book, you can. If you do not want to read the book anymore, you do not. So that is not what we are not concerned about, but we are just saying that the stack works in the same way, almost like the same way. So what happens is, in a function, just say that this is the part of memory or the RAM which, okay, let me say that both of these portions of the memory are stacks. So in the perfect world, or in the case of RAM, these two are sitting on top of each other. So this is not two different RAMs or different stack frames or stack, they are actually on the top of each other. So in this case it would be something like this, and this would represent basically this stack frame. So what is happening here in case of a computer function, this is, let's say, the portion of the stack memory that has been assigned to the function main. So every variables within main, every return addresses, all of these things are stored in those memory cells or those stack positions. All right, so as soon as we are done reading or doing any actions with the stack, we can easily clear the whole stack frame. And the most important thing is, when we are already on this stack, we can immediately shift to another function of the same program which may be residing on another portion of the stack. All right, so when we are done with that portion of the stack, we can easily come back to what we were doing in this portion of the stack which is assigned to main. All right, so these things, these pieces of pages, as we have written that this is the return book that we are going to study, is written in this piece of paper. This is the piece of paper where it says which book, or what is the number of the book that we are going to study in this bookshelf. All of these things are little pieces of memory that resides within the CPU to hold only this kind of information, and these kind of memories are called registers. So registers are actually very fast. They reside within the CPU. Their job is to basically provide the CPU with values, numbers, and information, and maybe pull information to and from the memory and the CPU. So now, as we are done with the analogy, we are going to build a real stack frame based on this program. As you can see, this is a real basic program. That is, the main job of this program is to add two numbers. So in this case, we have two different functions. So this is the main function. What we are doing in the main function is we are initiating a variable called a, and initiating the variable with a value 5. Then we are initiating the variable b and initiating with the value 5 as well. Then we are initiating a variable c, and within c we are storing whatever the function add is going to send or return. So I really hope that the camera is focused. Anyways, so in this part you can see that we are calling this function called add, and we are providing two variables as the parameters. And after this is done, we are basically printing on the screen anything that is stored on the C variable, right? So in the add function, you can see that as soon as we are calling the add function, it will immediately jump to this function right here. So in this function, nothing is done, anything complex. So what we are doing is we are taking the a and the b, which were the parameters for this function. We are adding those two parameters and keeping the value in the integer variable called c, and after that we are returning the c. So you can see from that if a was 5, b was 5, then the result of the addition would be 10. So the 10 would be stored in c, and it would be returned. So you can see here in the main function, int c was meant to be whatever the return value is from calling the function add. So the return value is currently 10, so int c is going to be basically initiated with the value 10, and it will be printed on this line. So I'm going to be going to the next page and manually drawing the whole stack frame for this one. And let me just give you again that I'm not going to be particularly describing an Intel format assembly or AMD or AT&T format assembly. I'm not going to be doing any encoding. I'm not going to be doing any binary or hexadecimal things. I'm just going to be saying everything in layman's terms, and I'm going to be skipping some steps because we don't need every step to understand stack frame. Maybe to understand assembly and how the CPU registers work, that would be a part for another chapter. It's actually very easy. That's why I'm not going to be going on that, except the one or two examples at the first positions of the explanation. Anyways, so let's go ahead and draw up a basic stack frame where the memory addresses are worth of 1 byte, and I will just name the memory addresses 100, 99, 98, 97 just for the ease of understanding, because we do not need binary and hexadecimals just to understand the analogy, right? Okay, so as I was saying, I will not be doing anything vendor specific, that is Intel's version or AMD or AT&T's version of assembly, but I'm still going to say that the way I'm going to use the command is more or like on the side of Intel's way of doing assembly. So okay, so first let me draw up the stack, and pardon my drawing skills. Let me just build up the stack. There it goes, and let me give each of these stacks a memory address, and each of these are a section of the memory. Okay, so just let me say that I'm doing the examples in such a way that each of these addresses cost exactly 1 byte. So each of these spaces are made up of exactly 8 bits or 1 byte, whatever you are comfortable with. So let's make up the stack. Okay, now as the stack frame is done, let me give them an address. Now just remember that in case of Intel, memory addresses grow from high addresses to low addresses, alright, which means if this memory address is 100, then as it grows up, it grows to lower memory addresses, alright. So this would become 99, 98, 97, 96, 95, 94, 93, 92, 91, 90, and 89. Right, and this 100 is the highest address, right? Which means that this is the top of the stack, and in this particular stack section of the stack, this is going to be the lowest address here. All right. Okay, now let's drop the stack for the program that I just showed you, that is adding of two numbers that includes a function call and a return address. Okay, anyways, so let's start with the first instruction that the assembly executes is something called push BP. Now what does this instruction mean? Okay, so let's break up this whole instruction and let me explain what each of these two things mean. So push is a stack proprietary instruction, and what it basically does is it pushes to the stack anything that is written after the push instruction as an operand, right? So what is BP mean, or in this case what I like to call the base pointer? So if you remember in the last analogy that I was showing you using the copy and the pen, that there is something called the start pointer, right? So if you were going to the library or the bookshelf and you know that you are going to start from the third book, and that third book is going to be the start of your journey towards reading 4 books in a single day. So in that case, that was called the start pointer, which I actually said in that analogy. The start pointer and the base pointer acts basically as the same thing. So base pointer is going to be the pointer that is going to be the start position of the function that is going to be executed right now. All right. So what push does is it immediately pushes the base pointer on the top of the stack. There is another interesting thing right here. There is the special register in the CPU called SP, or what we call as the stack pointer. So the job of the stack pointer is to always remember the last used position in the stack, which means where is the top of the stack right now after a lot of pushes or pops. So before pushing the base pointer, the stack pointer was pointing right here. Alright, because as you can see that, as I have already told you, that this 100th address is now at the top of the stack, and the job of the stack pointer is to always remember what is the top of the stack. So in this case, stack pointer is currently pointing at 100. Alright, so let me make up a little register in here called the stack pointer. So just let me say that this is the stack pointer. The current value of stack pointer is 100. Am I right? Nice. So whenever we have pushed the base pointer, now what value is the base pointer right now? The answer is I don't know. The base pointer might be having the value from some previous functions or some previous usage of the base pointer, or something that we have modified or not. Maybe the compiler modified it, I don't know. So what the base pointer is, we don't know right now, but we still need to keep that in mind, because after the program is done executing, we need to go back to the base pointer to exactly know where it came from and return to what it was doing. So the base pointer, the current base pointer might say, let's say the current base pointer has the value, what am I writing? Let's say that the current base pointer is at 25. I don't know what 25 does, right? So what I'm doing is, when I'm executing the instruction push base pointer, what is happening is the value 25 is going to be saved regardless of whatever it means. So as soon as the base pointer is pushed onto the stack, what happens that the stack pointer immediately grows, or in this case decrements by 1, because the stack pointer is just now filled with the base pointer, right? So if it is filled with the base pointer, this is not the stack pointer anymore, or this is not the top of the stack anymore. The top of the stack is now representing this 99th address, right? So in this case, what happens is the stack pointer is decremented by 1 and is now pointing at the address 99. So in this case, the stack pointer is immediately going to be changed to 99. Now this is going to be the start of the function. So what we are going to do here is we need to take a note of what is the stack pointer currently is, because we need to pull up some space for the functions to run. So in our case, we have just taken 3 variables, right? A, which represents 5, B, which represents 5, and C is going to be holding the total added value of both A and B. So we have space for 3 variables, and for emergency we are even taking another one. So let's take 4 memory addresses out of the stack and assign it to our function main. Alright, so as now the stack pointer is currently pointing to 99, which is also saved on the stack pointer register here. Okay, so the base pointer is now at 25 and the 25 has been pushed. So we have already saved the previous value of the base pointer and we do not need this value right now. What we need is that we should copy the value of the stack pointer to the base pointer, and the reason is that when we play with the stack pointer, the base pointer still remains the same as the stack pointer is right now. So the command would be move bp sp, which means move to base pointer whatever it is in the stack pointer. Alright, so what is happening is, as soon as I have done executing the command, the base pointer is going to be deleted in the register and would be replaced by the value 99. Alright, now at this part, when we were executing this particular instruction, nothing was changed onto the stack frame because we are not using the stack right now. So as we are done with copying stack pointer's address to base pointer, we are going to be doing the next instruction, which is making the space for the variables that we will need to store later. So for that, what we need to do is to take 1, 2, 3, 4 pieces of memory addresses and make it empty, so nothing can change these 4 addresses except us as a programmer, which means if we intentionally change one of these 4 addresses, then we can only change the values. Except that, no interrupts or no system calls or no other functions can change this portion of the memory. Now to do that, what we need to do is decrement this stack pointer by 4 places. So the command would be sub sp maybe 4. Now what this means is subtract stack pointer, whatever it is in the stack pointer, by 4. So as soon as we do that, the stack pointer is going to move 1, 2, 3 and 4. So the stack pointer is going to now point to particularly this address. Alright? Okay. So if we calculate, 95 is the address where the stack pointer should now be. So the stack pointer is going to be replaced by 95, as the control unit is treating this memory location as the pointer of the stack currently, because we just moved, or we just altered the value of stack pointer to be or to hold the address 95. So as of now, the base pointer, which is this one, is holding this particular cell, and the stack pointer is holding this particular cell. Now the difference between these stack pointer and base pointer, that is this region, is going to be the stack frame that has been made only and exclusively for the main function of our program. Alright, so just let's subtract this, maybe this as well. Now the next command would be to store the value 5 in this memory cell, and the way to do that is we are going to reference the base pointer, because the stack pointer can move by itself. So if another programmer or another function calls anything or pushes something on the stack, then the stack is going to be decremented and or incremented according to what the programmer does. So we cannot exactly trust the stack pointer, because the stack pointer is in constant motion. But on the other hand, base pointer is at 99, and until and unless we change that value manually, the base pointer is always going to be pointing to 99. So we are going to be using the base pointer's value as a reference to address the memory. So this particular command, that was a equal to 5, is going to be doing in assembly as mov. Now this mov function, what mov does is basically it acts more like copy, but in assembly we use move. So mov the location EBP currently, BP 5. So as soon as we do that, in the location BP, 5 is going to be stored. So BP is not directly accessible. The reason being, the BP's value is 99, and what is 99? We do not know. The meaning of 99 we yet do not know. But if we actually give a square bracket, this means that we are talking about something or some value that the BP holds is talking about the memory. So what means that BP is currently at 99, right? So as soon as we do a square bracket, we are specifically telling the CPU that this 99 is a memory address. If we remove the square brackets, the 99 does not mean anything right now. Okay? But when we are just applying the square brackets, this 99 is going to be treated as a memory address, and as soon as it does, it knows what the memory address is for 99, so it will immediately go and store 5 on the stack. For the second value, or the second instruction for this addition program, is still going to be another one, that is move BP -1, and then again 5. Now why -1? The reason being, in the exact location of base pointer, we already have stored 5. Am I right? So this position is filled. We cannot use this position anymore. So the second position would be this free memory, right? So in that case, that is going to be base pointer -1. So what is base pointer? 99. So 99 minus 1 is 98. So whatever it is in the memory location 98 is going to be replaced by 5. So we can see there is nothing right now, but it will become 5 because we are going to move whatever it is at the address 98 to 5. So again, the 5 will come here. Alright, now what happens? What we do, that is, I'm not going to be going to detail into, that is, we need to copy these two values to a CPU register, or what we call as a general purpose CPU register, for it to work with addition, subtraction, or any kind of math operations, right? So the syntax would be easy, that is, move, maybe there is a register called A, so move A, again EBP, and this is going to be a memory address. So this basically means move whatever it is in the address EBP, which is in this case currently 99. So it's telling to telling the CPU that move whatever it is in the address 99 to A, to the register A. So whatever it is at 99, we can see that it's 5, and this 5 is going to be copied to the register A. For the second command, it would be again move B, BP, or base pointer -1. In this case, base pointer -1 is 98, because 99 minus 1 is 98. It's as simple as that. So in the address 98, we have 5. So this 5 is going to be moved to B. So now the CPU registers A has 5, B has 5, and we will use the registers ESI and EDI, which is basically source instruction and destination instructions. So we are going to use those two registers to send the values of A and B to the function. Now this is the next part, is going to be very important, that is the function call. All right, okay, so in case of the function call, what happens is, at this point it is going to be calling the function add, if you remember. So if we call add, then it is completely going to jump to completely another stack frame. Am I right? So how will the control be given back to the main stack after that add function is done with? Now that is the important or interesting part. If you remember that the stack pointer is currently pointing at 95, which means the stack pointer is 95, which means that this is the part which is now considered as the top of the stack, right? So in that function, there would be, in the function add, there would be another set of push, base pointer, move, stack pointer, move, base pointer, stack pointer. Again, that kind of thing is going to happen. But before that, when we particularly use this instruction call, and there would be an address, so I'm just not going to write add. So whenever we are trying to call add, now this add may be in a completely another section of the RAM. Maybe I draw a small RAM here and say that there is this instruction 501, or there is this address 501, right? So let me make this clear. So there is this address 501, maybe 502, 503, I don't know. So we maybe in the address 501 there is this function called add. So whenever I'm going to call add, whatever is going to happen is that the compiler, or in this case the CPU, directly go to this address and start executing from here. Now how it is going to remember, if you remember when I was talking about the bookshelf analogy, you wrote that information in a piece of paper, that when you are done with reading the book from the second shelf, how are you going to come back to the book you were reading on the first shelf. So that piece of paper we spoke about in this case is also a register, and that particular register is called the instruction pointer. Now the instruction pointer is a register whose basic job is to increment by 1 each time a loop or a CPU cycle is completed. Alright, so if for example the current value of the instruction pointer is maybe 5, so on the next CPU cycle it will be incremented to 6, on the next CPU cycle it would be incremented to 7, on the next CPU cycle it will be incremented to 8. So this is the basic job of the instruction pointer, and these values are basically memory addresses. So the address is incremented by 1 on each CPU cycle completion. So in that memory and this memory address, so for example 8 in this case is the memory address. So what CPU does is whenever the instruction pointer is incremented and that current value in this case which is 8, the CPU is going to directly jump into the 8th address of the memory and execute whatever instruction is stored on that memory address of that memory. Alright, so when I'm calling add, okay, so when I'm calling add, let's say that the current instruction or the current memory address that the instruction was being read from is, say, let's say current instruction is maybe 202. Why not? So if the current instruction number or the current instruction address is 202, then what call does is it immediately pushes this value that is currently on the instruction pointer 202 to the stack. Now if you remember, the stack is still pointing at 95, which means this address is now considered as the top of the stack. So whenever the call instruction is executed, the call instruction by itself pushes the current value of the instruction pointer register to the stack, which means that this 202 would be pushed to the stack, and this will again go up to here. So now the stack pointer is pointing to 94. Am I right? So this 94th address is now considered as the top of the stack. So if I just delete these, now the stack pointer is pointing to 94. Right. I hope you can see everything. So now what happens is we are going to do the same functions, or we are going to perform the same instructions that we did on the main functions, but we will do the same things now for the add function. So in the add function, we are again going to go for push base pointer. If you remember, in the main function start, we also did the same thing. So push base pointer. So if you currently remember that the base point is still pointing at 99, right? This 99 is still the current value of base pointer. It's immediately going to push the base pointer on the stack, which means this is currently 94. You can see is now the top of the stack. So the base pointer value, which is 99, is immediately going to be pushed onto the stack. So the stack pointer value is now pointing to this particular memory address. So this 94 is going to be replaced by 93, because now the stack pointer is pointing at 93 and 93 is going to be considered as the top of the stack. We are again going to say that move base pointer stack pointer, which means the current stack pointer's value is going to be copied on the base pointer, and again in this case the stack pointer is pointing at 93, which means the base pointer will become 93, and again we are going to subtract stack pointer by 4, maybe, why not? So again 1 2 3 4. So now this is going to be the stack pointer current location. So the stack pointer, let's say the stack pointer is going to be replaced by 89. So 89 is now currently considered at the top of the stack, because of course if the board was wide enough, then I would have drawn more stack lines or stack addresses right there. But let's say that this is now currently the top of the stack, or you can also say that the memory address or the memory space is coming to an end. Anyways, so 89 is now the current value of stack pointer, and this whole region starting from 93 to 89 is going to be assigned specifically for the function add. So in the add function we are doing the same things again and again. So again we are going to copy the value of a, which is 5, and we just got the values of a and b from the parameters that main has sent to the function add. So again, by the same way, that is, move, okay, one thing that I have actually forgot to tell you, maybe not forgot, but I have missed, that is, if you remember that these two values on the previous main function was copied to register A and register B, and then it was again transferred to SI, DI, whatever. So these two particular registers currently hold the values 5 and 5. Am I right? So this is where we are going to use the registers back again. So what we are going to do now for the add function is move again base pointer on square brackets because this is an address, base pointer SI. So SI, or source instruction, had this value 5, so immediately 5 is going to be stored in this memory address. Again move BP minus 1 DI, 5 is going to be copied here. Then what we can do is execute the same instructions over again, that is let's take the values from the memory addresses onto the CPU registers. So move A, maybe again base pointer, so thus this 5 is immediately been copied to A. Then again move B, BP minus 1, again then this 5 would be copied to B, and after that the particular instruction for performing an add operation is simple as just add. So if we just do add A, B, what is happening that A had 5, B had 5, so the value at the added value 10 is now being copied automatically to A, or in this case what I can specifically say is that the added value is now updated on A. So the A is now holding the value 10. So we can again put this A's value onto this memory location by just saying move A, okay, not here, so move BP minus 2, because BP minus 2, if you notice that BP's current value is 93, so 93, 92, 91, 93 minus 2 would be 91, BP minus 2, which means 91. So move into the address 91 the value of A, which is currently 10. So as soon as I do that, this 10 will be copied to 91. Now if you remember that we have done on the C program that we have returned the added value to the main function, right? So in that case, it's just simply what it's going to do is again copy the value of 10 to one of its registers. So simple as move A BP minus 2, which means 91, move it to the register A. So this A register is going to be having the return value. So whenever we come back to the main function, we are going to use the value that is currently stored in the A register of the CPU to pass it to what we have called the C variable in the C program. All right, I know it sounds a bit confusing. I'm using multiple versions of A, B and C, but you just have to remember that the A, B and C's of the assembly program just mean registers, whereas the A, B, C on the C program, they just mean the variables. So all I'm talking about currently is now the registers, but when we are performing the return C on the add function on the C program on just this context, that is when we were doing, for example, return C. So the C currently has the value 10 right now, and on the main function we were doing C equal to add A, B. So this C will be returned from the add function and the C will hold the value 10. So in the language of assembly, this C will be taken from the CPU register A, which has just now been copied from the memory address 91 to a CPU register A. So again, this part is also not that much important because the moving from registers and moving to and from registers and to RAM is pretty much simple. Now the interesting part starts now. So as you can see that we have used up this whole stack frame, that is the job for this particular stack frame is over with, because the job for the C function add was just to take the two parameters sent from main, add them, return the main, the result of the addition. So all of these jobs has been done with. So we have no use of this current stack frame anymore. So how do we delete this stack frame and go back to what we were doing in the main? Because if you remember from the C program, the printf part, which is displaying the value of C, or the displaying the value of the added result on the screen, was still done on the main function, not on the add function. So how we are going to go back to the main function? Now the interesting part begins. There is this specific command called leave, or specific instruction called leave in assembly. The job of leave is to revert the actions on the current stack frame that is done by the current function, and when the function has been ended with, the job of leave is to revert whatever changes have been done to the stack frame. So what are the changes that has been done to the stack frame? We have used this memory address 91 for a value, we have used the memory address 92 for a value, 93 for a value, we have used this 99 and 202 for something that we do not know apparently right now. Then we have modified the value of ESP to point to 89, we have modified the value of base pointer to point to 93. So these are all the changes that has been done for the function add. So how are we going to revert this? Pretty simple. If you know that the command to make this stack space was to subtract 4 memory addresses from ESP, right? Okay, pardon me if I'm saying ESP or SP sometimes, because when I studied this thing, I studied specifically for x86, and in x86 the stack pointers or the base pointers, all of them starts with E prefix. So EBP means the base pointer, ESP means the base pointer. In 64-bit architecture, RSP means stack pointer, RBP means the base pointer. So the BP and SP part is common. So just keep note of that. If I am mistakenly saying EBP or RBP sometimes, pardon me for that. Just remember that whatever ends with BP or SP is basically means the stack pointer or the base pointer, maybe just the amount of memory address it can address at one given time increases or decreases, but we are not actually studying about that right now. So all of these changes is going to be reverted. How? We have already decreased or decremented stack pointer by 4. So to revert the function, we have to increase the stack pointer by 4 to come to point to this particular memory address, right? So one of the way is to basically add 4 to the stack pointer, or if you remember, the base pointer is currently at 93, or this memory address, which is also the start of the stack. So either we can add stack pointer with 4 memory addresses, or we can directly copy the base pointer to the stack pointer, which will basically do the same thing. So let me just rephrase here. Stack pointer plus 4 equals what? So stack pointer is currently at 89. So 89 plus 4 is 89, 90, 91, 92, 93. Also, the base pointer is pointing at 93. So doing stack pointer plus 4 equals 93, or doing the same as move stack pointer base pointer is going to be doing the same exact action, right? Because the base pointer's current value is 93 is going to be copied to stack pointer, which means that we are doing the basically same thing. So let's do the same things and write in exact comments as it would look in assembly. So move SP BP basically closes this whole gap which we have taken for the function add, and now the base pointer and stack pointer is pointing to the same exact location, that is in this case 93, right? So as now this has been closed, which will currently mean that this is considered, or the address 93 is now basically pointing at the top of the stack. So as you can see, all of these things has been cleared out. These mean nothing now. These are empty spaces, because now the top of the stack is representing 93. So now we have basically reverted the actions that has been done on the stack for the function add. Now what we are doing manually, that is move stack pointer base pointer, is not what we are actually doing, because this basically represents the instruction leave. So when we call leave, what happens is that this is exactly what is going to be executed. So we are just going to say leave, and whenever I say leave, this whole stack frame is going to be deleted, and the stack pointer will be pointing to 93 now. The base pointer is also going to be pointing to 93. Now, very important part, pop, maybe say A. Okay, not A, because why not A? Because if you remember, A is now currently holding the return value from the add function, so we cannot use A, so let's use B. Okay, now what is exactly happening? Pop is basically a stack function just opposite as push. So if you remember, push basically pushes whatever value on the stack, and pop pulls out whatever is on the stack to another register. So pop B means whatever it is at the top of the stack is going to be pulled out and kept on B. Alright, now there is this specific thing that you need to know. In case of stack, we use something called a last in first out data structure. So what exactly happens is, this 99 was pushed second, this 202 was pushed first. If you remember from the previous lessons, that 202 was pushed first, then 99 is pushed second, so this 99 was pushed last. So when we are performing pop B, 99 is going to be the first one to get out of the stack and get copied to the B register. So when I am performing this command pop B, 99 is going to be copied right on B. Okay, now as soon as the pop has been executed, this 99 is also going to be cleared from the stack, and now the stack pointer will be pointing to 94, which is currently considered now as the top of the stack. So now the last function would be ret. Now what ret or return does is very interesting by its own way. What it does is that it returns anything that is on the top of the stack. Now where should it return? It basically gives the value to the instruction pointer. So the total job of ret is to do two things: pop whatever it is at the top of the stack now and copy that to the instruction pointer. So whenever we perform the ret instruction, from the top of the stack, which is currently at now 202, is going to be popped off to ret, and this 202 is going to be copied to the instruction pointer. So 202 is now at the instruction pointer, which means that the CPU will on the next cycle immediately jump to this 202 address. So what's in 202? So if you remember, when I was talking about the main function, when the call was actually performed, or when the main called the add function, that particular instruction number within the RAM or the memory address from where the instruction has been pulled off was currently residing at the memory address 202. So we pushed the 202 to save the current state of the instruction pointer, if you remember. So that was pushed on this stack address. So this 202 is now given to instruction pointer, which means on the next CPU cycle, the CPU will perform directly whatever it is at 202 memory address. So what is it at 202 address? The next line, which we would have performed in the main function if there was no call happening. So I will rephrase that right now. If there was no calls from the main function, the next instruction address would have been 202, but we did call the function add, so that 202 was saved on the stack for use later, which that later just arrived. So when the call add or the add function has been done with, we are returning that 202, we are popping that 202 off to instruction pointer, and the CPU will start executing whatever it is at 202, and in 202 address of the memory, the remaining portion of the main function which was not being executed because we called the add function is now going to be resumed with. Now if you come to this part, you can see I have done pop B, but I have just done pop B because at that point I didn't remember that in this case B was going to be acting as a base pointer. So I'm just going to delete this b and replace with base pointer, because that time base pointer was at 99, I guess it was. So the pop bp would have immediately taken the value 99 from the address 94 and copied it to the base pointer. The base pointer is now replaced with 99 again, and we do not need to worry about the stack pointer, because the stack pointer can be wherever it wants to. We just only are concerned about the base pointer, because this base pointer is what we are going to reference to store or retrieve variables from the stack frame. So the base pointer is right now pointing at 99, which was actually happening before any of these things happened. So as you can see, we are back on using the original stack frame that was called from main, right? So we are now currently performing in this zone, which is specifically allotted to main. So this is how a call is performed. So we went out from the stack frame, we made out a new stack frame for the function add, we performed calculations and actions on the stack, we added the values, we got 10, that 10 has been copied to another register, we deleted the whole stack frame, we restored the previous base pointer, which is 99, we have restored the previous instruction pointer, which was, I guess, yes, 202. So everything is done on this part and can be considered not important anymore. So all we need to care about right now is what was remaining in the main section before we called the add function. So after that part, it's not very much important, because what we are basically doing is we already have the value, the added result, or the return value, which is 10, in some register within the CPU called A. So we can easily go and store move BP minus 2 A. So immediately the 10 will be copied to this location, and we can call a printf function and display this particular memory address, or we can again retrieve this value by saying move, okay, just let me remove some of these lines. So move A BP minus 2, and then we can send this A to the printf function, and the printf function will thus display the value 10 on the monitor. And after that has been done with, again the same things will be done to clear this stack frame. So we have already cleared the stack frame for the add function over here, and now as we are done with the main function, we are going to do the same things, that is deleting this stack frame as well. So again, leave will be the command to clear or revert the whole actions that has been performed on this part of the stack. Then again, we are going to pop the base pointer value, or the previous base pointer value, to base pointer. So even before the main function has been called, the base pointer might have been on some other functions. So that function is, I guess, still now incomplete. So we need to go back to that current function. So for that, we need the base pointer value of that function on the stack, so which we do not know about. So maybe 25 is what base pointer was before we made this stack frame. So pop BP will immediately pull this 25 off to the base pointer, and the base pointer can return to whatever it was doing before any of these actions happened. So this is basically what stack pointer looks like. And if I again brief the whole thing in a very little speech, I would just say, in a stack pointer, we push the base pointer, we copy the value of the stack pointer to the base pointer, we move or decrement the stack pointer in such a way that we get some space for the local variables. We use those spaces for the local variables. We can, if we want to call another function, then we can create another stack frame for that function. We can work there, we can clear the stack frame, we can pull off the values which was saved that's needed to come back to this main function, and we use that values to come back to the main function. And after the main function has been done with, we can clear out this part as well and let base pointer go back to whatever it was doing before any of these things happened. Alright, so I am done with the board and pen. For the last time, I'm just going to go over to my computer and show you hands-on whatever I have just taught till now on a debugger. All right. Okay, you can see the same program that I have written in C on my pen and paper is typed up right here, and the debug deassembled version in this case is right here. So you can actually see what I have taught you is basically what it is written right here. So you can see that we have pushed the base pointer or register base pointer in this case. Just forget about the R or E prefixes because that is assembly specific or vendor specific. So again, we have pushed the base pointer, we have moved the base stack pointer's value to the base pointer, we have decremented the stack pointer by 16, then we move this 10. In this case I have taken the variables, I guess 10 and 20, not 5s. So anyways, so move the value 10 on this memory address, that is base pointer -4, move the 20 on base pointer -8, then copy these values from the memory addresses to EDX, then the second value to the EAX, and then give those EAX or EDX values to ESI and EDI, then call add. As soon as we call add, the same things are happening again. We are going to push RBP. Now you can see that there is no explanation for call. So whatever happened in the call, I have already showed you on the board that what call does is it takes the current information, which is this instruction. So if I just say that this 26 is a memory address, for example, this is not, but just let's say that this 26 is a memory address, this call instruction is immediately going to store this 26 to the stack, and then it is going to immediately jump to wherever location the add is residing onto. In the add section, again we are pushing the RBP, we are making the stack spaces, we are copying RSP's value to RBP. In the same way, we are taking two memory spaces for two variables, then we are copying those memory addresses values to those registers, then we are adding those two registers. After that, we are storing that added value to the memory, then again popping the value off from memory to EAX, and that EAX is going to be holding the return value. Then we are going to say that pop RBP, which means the RBP is now popped off. Now we did not actually use this leave instruction, but as I said that these things are mostly vendor specific or instruction set specific, so I don't care about that. So again, the previous saved base pointer is popped off from the stack and stored into the base pointer register, and return is basically returning or popping of that current value, which is 26. If you remember, I have already said that 26 is the memory address that call is immediately pushing onto the stack when we use the instruction call. So this return function will immediately pop off the value 26 on the stack, and that 26 is going to be copied to the instruction pointer, and that instruction pointer will again resume its job from this line. So you can see that in this case we have stored the return variable in EAX, and in here we are just retrieving whatever it is at EAX to RBP -12 memory address. Then again we are popping whatever it is at RBP -12 memory address to EAX, and then we are using the ESI register again to send those values to printf. And after the printf has been done with, we are basically clearing the stack, or what we say as, reverting the stack. Again, we have used leave, as you can see. So the leave and the return is going to be doing the same thing as it did in here. So in this case, the return is going to be giving register base pointers, or the instruction pointer, the previous values before any of these things have happened. So before any of these functions has been executed, maybe the RBP or the instruction pointer was busy doing some other job. So as soon as this job is done with, these return, and this return will make the instruction pointer and the base pointer go to whatever it was doing right before any of these things happened. Okay, so I guess I have done maybe a confusing but a good job at explaining the stack and the stack frames. So I guess that this video or this tutorial will help you in some way or another. So before I come up with another video, maybe on exploit writing or reverse engineering, have a good life. Goodbye.